Okay, good evening and welcome back and Happy New Year to all of you. Before I forget, just three small things, administrative things. For all your courses, you have to fill assessment evaluation or something on TACT. Please do it seriously for all your courses. I know it takes a few minutes, but it's important. Second thing is next week, and it's a last course next week, there will be somebody from the public office of Nagoya University who is going to take some pictures. So it's good if you come. Of course, if you don't want to be on a picture, you can avoid to be on it, but I encourage you to be on it, and it will be used by Nagoya University for some advertisement. So please come next week. And about exam. Okay, so I'm going to give you a list with your names. Tell me, or just write one on each line, if you prefer to have an oral exam, or if you prefer to only go on with reports. I will contact you after. But if you have already submitted a few reports, probably you don't need to do an oral exam. If you prefer to do an oral exam because you haven't submitted any report, just mention it. And also, I would appreciate if you tell me which week you would prefer, because I don't want to interfere with the other exams. So if you can indicate, I think we have to submit the grade for February 12th. So I would prefer before February 7 or 8, but you can tell me I would prefer this week. So just tell me, give me some information, and I will contact you individually. Okay. And if you are online, we will exchange by email. Okay, so what we did last week. There are many things on the blackboard. I will go quickly. First, we studied the notion of geodesics, which are special curves satisfying a second-order differential equation. And it turned out that if a curve realize a minimal distance between 2 points P and Q, then this is a geodesic. But it's very important to state it correctly. If a curve realizes this minimal distance, it's a geodesic, because this distance can sometimes be not realized by a curve. So it's a geodesic when you take the arc length parametrization. Then I mentioned this theorem, which is rather important because it gives you 3 or 4 equivalence notions, and one is a notion of geodesically complete, one is a notion of metrically complete. You can check the statement, but it's important because if you're in this setting, it gives you the existence of minimal geodesic between any 2 points. So this is a right framework for having geodesics between 2 points P and Q. Then we studied 2-dimensional manifolds in R3. This is an easy system because we can visualize it easily. This is a 2-dimensional manifold on R3. So what we can do on every tangent plane, we can still draw a vector which is perpendicular. So if you have a tangent plane at one point, you can still draw a vector which is perpendicular and take it off norm 1. Then if you, in addition, consider a curve going through a point P and with a velocity or tangent vector equal to xp, you can also consider these normal vectors along the curve. So define this function n of t as a normal vector along a curve. So it means if I take this curve, I would consider vectors like this, all of norm 1. And then we define a map between, take a tangent vector, so it defines the curve at one point, and send it to the derivative of this normal vector. And we have seen that this derivative is also a tangent vector. So it means for any xp, you associate another vector, which is also in the same tangent plane. So it means you can think about a matrix, taking one vector to another vector, and it is a symmetric matrix. Last week, I probably only mentioned self-adjoint or Hermitian, but it's also symmetric. It's the same. And whenever you have a, because we are dealing with something of dimension 2, whenever you have a linear map of dimension in a space of dimension 2, you know that, which is Hermitian or symmetric, you know that you have two eigenvalues, and I call them K1 and K2. You can choose one is bigger than the other one. And if you want to think about the interpretation of this expression, you have to look back at the Frenet frame, and this expression is nothing but what I call in this framework the curvature. So what does it mean? It means take a point. Okay, I take this point which is at the intersection. I can construct many curves. In fact, I can construct a curve for each vector on the tangent plane. They define, each of them define at least one curve. And we can associate these quantity. And we end with a family of curvature, a curvature associated with each direction. And in fact, K1 and K2 correspond, so the K1 and K2 correspond to the biggest to the extremal value, sorry, the biggest one and the smallest one. And all the other ones are in between. So it means that every point you have two specific directions. One gives you, with this expression, the maximal value eigenvalue, and the other one the minimum eigenvalue. So you have to check in the notes. Now we can also define both the product and the mean value, and they have a meaning. The first one is called Gaussian curvature. The second one is called mean curvature. So these two quantities are really associated to every point on the manifold. Then I mentioned a few other things. One, it's a Bianchi identity, and another one is about this curvature tensor. You can express it in terms of the gamma function. So this is a bit technical. And what is important, and it's important to realize it, we define, so we have this curvature tensor field, because whenever you define it with tensor field. And if you deal with a Riemannian manifold, you can even construct something more complicated, because you have this phi, which is this inner product. So you apply the curvature tensor field to an additional vector field and take the scalar product with another vector field. But I mentioned that it is C infinity of M linear in each argument. What does it mean? It means if you put a smooth function in the front of any of these vector fields, so if you rescale the vector field, you can think about this as a rescaling, then it's the same as taking out in front. So it's not only linear, but it's linear with a coefficient which is a smooth function. And there is a rather deep theorem which says whenever you are in this framework, this quantity evaluated at P, and be careful, it depends on 4 vector fields, so it means it depends on 4 fields on this manifold, is the same as just one tensor evaluated at 4 points. So there is a big difference, because here you have an expression on 4 vector fields evaluated at 1 point, and here you need to know only the value of these vector fields at 1 point. But yeah, I mentioned the reference where you can see this, and it really uses the fact that you have this C infinity of M linearity. And that's why you will find not in the literature, you will not find Riemannian curvature tensor field, but only tensor, because you can compute it pointwise. Okay, and the same for this additional expression. And the last thing I introduced is what is called the sectional curvature, because this object R is rather complicated. So we can define it in a simpler expression. On the tangent space, take a subspace of dimension 2. Of course, if you are already in dimension 2, it means you take everything. But if you're on a manifold of higher dimension, you take a subspace of dimension 2. You can define a certain expression in terms of this curvature, Riemannian curvature tensor. And see, I already used tensor because I know this result now. And it turns out that this expression depends only on the two-dimensional space generated by x and y. It doesn't depend on the two vectors you choose for this plane. It only depends on the plane. And this has, again, some interpretation. First, if you know all of them, you know this R, which depends on four things. So you get something simpler because it's only depend on an object of dimension 2. If you know all of them, you know this tensor, this curvature tensor completely. But in addition, if you are in dimension 2, what we have computed it here corresponds to the Gaussian curvature. So it was quite dense, but yeah, this notion of curvature appears at many places. Okay. So let me go on today. I will just finish this section. Then we have one section which is maybe a bit annoying, but the last one about holonomy is probably more interesting. But the second one is also important. And of course, you can interrupt me at any time. So we are still in this section about curvature, and I want to define two more objects which appears especially in relativity. So we consider for an orthonormal. I take a basis which, when it's orthonormal, I call it F1P up to Fm P. It's a basis of Tp of M. So we take the tangent space at one point. This is the tangent space at one point, and we look at one basis, which is orthonormal. We are in the framework of Riemannian manifold, so we have the notion of orthogonality because we have an inner product. Okay. And now I take two vectors, xp and yp in TPM. We set. I'm going to set. It's not the same S, just be careful. It's a different one. They have nothing. SPYP. S is, I don't know why, but it's for Ricci, the Ricci curvature. And the definition should remind you something. It's a sum over J, 1 up to M, of R, FGP, XP. Okay. So I'm using this complicated object, which is this Riemannian curvature tensor. And look, I put two vectors which are arbitrary, and the other two are on a specific basis. Does it remind you of a certain operation? When you take a sum with two vectors, it's like a trace. Like, it's a more complicated setting, but it's like when you take the trace of a matrix, you take your matrix, you take only the element on the diagonal. So this operation, in fact, it's called contraction of tensor. This operation is a contraction of tensor, but you can think about it as taking a trace. And why this analogy is important? When you take a trace, you probably know that it does not depend on the basis. If you take your linear map and want to define the trace, you can do it in any basis. So it turns out that this quantity does not depend on the choice of the orthogonal basis I have chosen. That's why it's an important quantity. It does not depend on any choice. Wait a second. This operation. So taking this sum over this expression, this operation does not depend on the choice. For matrices, you know that if you do a unitary conjugation, it doesn't change the trace. You had a question?
Yes, the trace is invariant even in non-orthonormal bases, I think.
Not fully sure. Think about it, I'm not sure. Okay. So this is called the Ricci curvature, and it's a kind of trace or contraction of a tensor with 4 entries, so it becomes a tensor of 2 entries. And you can also rewrite it if you use, it's also equal to this Riemannian metric of R of F, J, sum. Where is the sum? You can also write it as this sum over J, 1 up to M, phi of R of F, J at P, X, P applied to Y, YP, and then scalar product again with FG. It's the same expression. And you can wonder if you can do it one more time. Can you contract this tensor? And the answer is yes. But similarly, we can define this sum J1 up to M of S, SP on FGP. FGP. So now I had a function of only 2 variables. Again, I use the same basis, but it's independent of the choice of the basis. But I put 2 times the same vector. I do the sum. And now it's only a scalar. It's called R of P, and this is a scalar curvature. I just wanted to mention these 2 expressions, this Ricci curvature and this scalar curvature, because in some equation of relativity, they appear. You should think about it. The starting point is either this Riemannian curvature tensor field or tensor, or just in terms of R without taking the inner product. So just you can also express it in terms of this curvature tensor field. So there are many things many definitions related to curvature. This is what you should keep in mind. There are many definitions related to curvature. They play a certain role. And in the notion of holonomy, we will come back to this notion of curvature. So this is all for this section about curvature. Now, section 6.3 is a kind of reformulation of everything. Pattern structure. Equations. I'm not sure that this is the most important section, but depending on where you look in the literature, people are working in this formalism. We will see it's a reformulation of many things I have introduced. In terms of it is in terms of forms. We will see. So what we do, we consider M a smooth manifold. And I'm going to consider a local smooth field of frame. So what is it? M, a smooth field of frames. So what does it mean? It's simply, I consider M at every point, I consider M vector, which defines the tangent plane, and so that it's smooth when you move on the manifold, at least locally. So we know one example. It means that x1p, when you evaluate at one point up to xmp, is a basis of TPM. And it depends smoothly on T when you move T on the manifold. Okay. And we know one of them. I always mention one of them. It is a coordinate frame example. But I don't want to use always this example. Example for U phi, a local chart, then what I called E1 up to EM, which is based on this local chart, is a frame, is a field of frame. Is a smooth field. And this is what I call the coordinate frame. But we can be slightly more general. So we don't mention only this one. It can be another, any one. For example, you could choose to take one which is always orthonormal, and it would have some good properties. Now, if you have a basis of the tangent space, you know that we immediately have a basis of the dual space. So the dual is made of linear functional on the tangent space. It's also a vector space of dimension m. And it was called the dual basis. So then we consider the dual field, or the is it the field of dual field of coframe of coframe. So what it is, it means a family which is denoted by omega 1. Okay, there is a small ambiguity. So I realized it when I wrote the note. So let me write it like this with one parenthesis. I could forget this parenthesis, but in a minute it would be confusing. So I prefer to have a parenthesis here. So up to Wm of P with, it's a basis of the dual space which is also a vector space of the same dimension, and satisfying a certain relation. If it is a dual basis, it satisfies that. It's a Kronecker delta relation, so it satisfies omega j evaluated at P applied to xk evaluated at P. Of course, you need to do it at the same point P. This is delta jk. So it's a linear map. You can apply it to such a vector, and it gives you 1 if j is equal to k and 0 otherwise. And observe or remember that omega k is a one form. It's a long time ago. A one form is precisely a family which can be applied to a vector, to somebody in the tangent plane. So it was a definition of a one form. Again, example which has been worked on by Tutai. It's called the coordinate coframe. And it's related, it's a dual of the coordinate frame. It's a coordinate coframe. And I recall one more thing. We have one more relation. And then I will make a remark. What is this relation? These are the Christoffel symbol. And this expression is a connection. So how should we read this relation? Remember, a connection is something which tells you how you go from one tangent plane to another one, and it allows you to define this parallel transport. This was the notion of connection. We have seen that if you are in a Riemannian manifold, there exists a unique one having a certain property. So you don't have any choice. I mean, while you can, if you are not in the Riemannian one, or if you don't want to impose this additional relation, you have in fact plenty of connection. It's only unique if you take this additional condition and in the Riemannian framework. But then this relation means this connection, you can compute it completely in terms of Christoffel symbols. But what is important to realize is that these Christoffel symbols, so these are function now. This is a function on the manifold, so it means this is a function on the manifold. So it means these Christoffel symbols are functions on M, so you can evaluate them at any P. But they highly depend on your choice of X. So don't think that they are, once you have a manifold, they are given. They depend on the choice you take for a basis of the tangent plane. This is important to realize. These Christoffel symbols, they are related to the connection, but they highly depend on your choice of the field of frame. So this is important to realize. Depend on the family x1 up to xm. If you change it, this is probably something you should remember about this course. The description in differential geometry is a local one always. So if you choose a certain basis, you choose a certain frame, then you have quantities. If you change it, of course, these quantities are different. Their properties remain the same, but the exact expression is different. So I wanted to recall this and now introduce a new object. Now we define again a one form, and they are called, so it's a new object, connection. They are called connection forms by, so what is the definition? It's going to be omega jk, some I from 1 up to m, gamma I j k. First, observe that it's indeed a one form, because this is a one form. This is just a function. And if you multiply a one form by a function, you still get a one form. So you have a linear combination. It's a linear combination of one form. So it's still a one form. And it's called a connection form. Okay. Then we can play a little bit. So it's a definition. I define a new object involving the connection through these Christopher symbols on the one form. So you can check that you can recover the Christopher symbol by the following relation. Simply take omega jk, apply it to xi. I let you play, you get. So you can recover the Christopher symbol simply because it's a dual basis. And for now, if I take a more general vector field, this is a general vector field. We have a basis of this vector field. Again, I multiply by some function. So this is a vector field. It's a decomposition of this vector field on the basis x1 up to xm. Then there is one more relation that you can obtain. Then the connection x applied to y is given by we have already seen something of this type some times ago. The exact relation is not important. At least you should check that it's meaningful. Whenever you have two indices, they should. Okay, we have no I on the left, so the sum should be on I with one on the top, one lower. We have also sum over j. Why is it meaningful? Remember, this is when we apply a connection to a vector field, it's again a vector field. It's a vector field like it's an element like this. X applied to a function is a function. We do a linear combination with vector field. So it's a vector field. Now, this is just one form applied to a vector field. So this is just a function, time another function, and a vector field. So it's again a vector field. So it's meaningful. We get, if you play a little bit, you get these relation. So what does it mean? I have defined a new object, and we can recover both the Christoffel symbol from this object and this expression. So it means we can recover gamma. I just write it like this, and this connection from omega, which order kj, the family of omega kj. I define a new object, but I can recover the old one in terms of this new one. I told you it's an equivalent description in terms of form. But now remember one thing, and I mentioned it before. This is true for any connection. I mean, these relations were true for any connection. Now, if I take the Riemannian connections, or Levi-Civita connection, there are two conditions which are satisfied. It's symmetric in the gamma, the two lower argument, and there is a compatibility condition with the metric. So for the Riemannian, so for special choice of connection, two conditions are satisfied. So you can wonder, oh, how do I see this condition in this new object, in this connection form? And there is a theorem, these properties, these two properties, they lead to a certain theorem, which is called structure theorem of Cartan. Cartan is a mathematician, a French mathematician, and he did a lot of work in this field. Cartan. Yeah. This is just something for any vector space. There is maybe even a report on this. You can clearly construct, I mean, the dual is by definition the set of linear transformation on the vector space. The thing is you have to show that it's of the same, it's also a vector space, and it has the same dimension. Yes, there is at least one report from Kato-san on the website about this. So yes, the question for infinite dimensional is different. But so this is more info. But for finite dimensional, yes, the dual exists and has the same dimension. Yes. And there is one more property for finite, that the B-dual, so the dual of the dual is, you can identify it with the original space. And I used this identification one time. Okay, in this framework, so I mean with the object I have just introduced, this framework, the connection forms, of these objects of the Riemannian connection, are the unique solution, So what I'm stating is I'm going to state two equations. And the statement is that if you solve these equations, you get these two connections formed. So what are the two equations? I'm not saying that it's easy. Maybe Ole, you can, since you work on this, you can try to understand this statement. Okay, so what is the statement? As I said, if we look at the Riemannian connection, we have two additional conditions. So, and we know that this Riemannian connection is unique. And it turned out that then the Riemannian form, or no, sorry, the connection form I have introduced before are the unique solution of this system of equations where, what is this? This was a one form, depending on the choice of your basis. You take its derivative and it's equal to this also field of coframe, veg, this one, and this is what you are looking for. And the second is a compatibility, the derivative of what is Gij. We have already seen it. It is this, it's I, it's J. So the metric applied to xj, xi, xj. And its derivative is given by, again, this expression. Okay, it's a theorem. It tells you at least that, yeah, if you know how to solve this equation, they give you uniquely these connection form. There is one more object. This section is rather short. And I will conclude in a few minutes. The second object I need to introduce, we also define a two form. It's called the two curvature form. It's denoted by omega KL. Some of which I didn't write. I and J. What is this? It's a two form because it's a wedge product of a one form and a one form. These coefficient, I mentioned them before, there's a coefficient of the Riemannian tensor. Here it's probably even Riemannian curvature tensor field because this is still a function. So you have a function and then these two form. We define these two form. And then there is a theorem of this type. Please keep just these two equations in mind, because as I mentioned, these two equations define completely these connection form. And now I'm going to write one more statement for this two curvature form. There is a theorem about this. Again, the following equality holds. And I call it 3 because I will then mention these 3 equations. Again, it's not really important. But what it said that this 2 form, which was defined in terms of this Riemannian tensor field, Riemannian curvature tensor field, can be expressed in terms of these connection form. And okay, the conclusion of this section is that equation 1 to 3 are called Cartan structure equation. Are called Cartan structure equation. And what we have done, we have reformulated both the connection and this curvature tensor in terms of forms. We have reformulated the connection, nabla, and the Riemannian curvature tensor in terms of one of the connection, one form, and this curvature and curvature two form. This curvature two form. Now it depends probably on what you want to do. Forms are useful because they can be applied to vector fields, and before everything was more defined in terms of vector fields. Okay. I wanted to mention it because depending on what you do, or if you use this in general relativity, you might need to go from one framework to another one. Essentially, they are equivalent. Okay. Now, I'm not saying that you should remember these equations. Okay, any question or remark? It was a bit technical, but it's good to know that we have seen forms. And remember, forms were important when we did integrals on manifolds. We have expressed an integral on manifold in terms of M form. They played a role. But okay. So we have seen them again. Yes.
How, like when you say ij equals 1 to m, are we going 1, 1, 2, 2, 3, 3? Or are we going now?
Up to you. You are going to sum m squared terms. Now you can take them in any order. It's a finite sum. So if you prefer to go in any order. When I write this, these two indices are independent. So you can write, in fact, you can write as two sums. Sum over I from 1 up to n, sum over j from 1 up to m. You have m squared sum, m squared terms. Okay? Yeah, this is a short notation for two sums. I have no constraints or no conditions between I and j. Now, if you want to go up to infinity, I don't know. This is for your future. Something more interesting, holonomy. And probably you have seen some pictures related to holonomy, at least on a sphere. Suppose it's a sphere. What is it? You draw a triangle on your sphere. You go triangle. And you go with one vector, and you do a parallel transport along this triangle. And you will, just to Google this, you will see that when you draw the parallel transport, you don't come back to the same vector, but there will be an angle. And for sphere, you can express this angle in terms of the radius and the area of the triangle. Now, on a more general manifold, this is what I'm going to introduce. But so there is, the idea is we do the parallel transport along a curve. And we know, yeah, okay, you can show this picture to everybody. This is a typical picture for this. They cannot see.
You can draw this on the budget. Oh, yeah.
On a sphere, you draw a triangle, and you take one vector, you do the parallel transport. And I'm going to cheat. And finally, there is an angle between your initial vector and the final vector. So this is the notion of parallel or holonomy. It can be introduced in the more general framework. So what we do, we consider C a curve on a manifold. And for simplicity, I'm just going to parameterize the curve between 0 and 1. Piecewise, it's a piecewise smooth curve on M. Piecewise smooth means precisely it's smooth, and then you accept that it's no more smooth on one point, on a second point, or on a third point. But still, it's continuous. And I will assume that M is connected. If M is not connected, if M is made of two parts, it has simply there is no path from one to the other one. Connected on Riemannian. I will assume that we are dealing with a Riemannian, even though I'm not sure a Riemannian plays such a big role. Okay. And I assume C of 0 is equal to E. I'll just, and now I consider a vector in the tangent plane at P. And I do the parallel transport along C. And I'm going to call it X of T. B is a parallel transport of XP along the curve. And we have seen that it's uniquely defined. This notion of parallel transport along a curve is uniquely defined. It's a solution of a one first-order differential equation. So it means xt is x at c of t, which is in t, c of t of m. At every point we draw a curve on this, and I start at a certain point, and I do the parallel transport along a curve. It's not always a closed curve, just a curve. And of course, x of 0 is my initial vector xp. So this is the framework. I'm not always considering a closed curve in this definition. Now set PC. It takes this tangent vector and send it to, so this tangent vector xp is the vector at time 0, and it send it to x at 1, time 1, and this vector is in T of C1 of M. Just take the parallel transport from time 0 to time 1. So PC maps this vector, which is the initial vector, to its image. This is the image of x0 after the parallel transport, along the curve. I just look at the final vector, and the map associating xp to the final vector is called PC. Now, what happens if you consider a first curve C1 and then a second curve C2? Then observation, which is, this one is trivial, observation. If you do PC2, PC1, this is equal to PC2 composed with C1 if C1 at 1 is C2 at 0. What does it mean? It means precisely you start with one curve C1, this is C1 at 0, this is C1 at 1, and then you continue with a different curve C2. And so this one has to be C2 at 0, and this is C2 at 1. This is quite clear. If you do the parallel transport and then along a second curve, you can just have this relation. But in addition, this is a bit more subtle. Here, C minus 1. What is C minus 1? It's going backward. C minus 1 is, this is C1 minus 1. You go backward. Okay, this is the notation we use in calculus 2. C minus 1, backward, is equal to PC minus 1, which is not completely trivial. But why you have it, so if somebody wants to study this, it's probably, you can do it. It's because the parallel transport I mean, this is the key argument, is given by a first order differential equation. The fact that it's first order is going to help you in this proof. But it's not completely trivial that going backward with one vector through this parallel transport is the same as the inverse of the map from here to here. No, Heavy, do not every minute one question, please. Let me go on a little bit. Except if you want to prove this. Now what happens if the curve is closed, if C is closed? What do I mean by closed? It means the initial point C of 0 is equal to C of 1. So we are dealing with a curve like this on the manifold. So we are on the manifold. And we have a curve like this. Then what we observe, look, PC is from the tangent plane at P to the tangent plane at P. Initial point and final point are the same. So you start with a vector, you do its parallel transport. I don't know if it is a parallel transport, but you do the parallel transport along this curve. Okay, you are going to do a better picture. Thank you. And so you started with one vector, you end up with another vector, but they're on the same tangent plane. This is a good point. You have your manifold, you draw a curve. Probably I should draw a curve on this one. Okay. You draw a curve, you do the parallel transport, starting with one vector in the tangent plane at one point, but you end up with another vector in the same tangent plane. So you can compare them. If they are not in the same plane, you cannot compare them. But if they are in the same tangent plane, you can compare them. And it turned out that this operation, if you choose a basis, it's an element of GL of TP of M. What is GL of a vector space? Set of invertible matrices, general linear map. And in fact, you can say even a bit more. What we know about the parallel transport, it preserves the norms. So in fact, it's even in O of TPM. This guy is inside O of TPM. What is it? It is called the orthogonal matrices. And it is inside the set of orthogonal matrices. And the argument is because it preserves the length. The length is preserved. The length of your vector is preserved. Because the parallel transport preserves the norm. It's not an arbitrary invertible map, but it's in the orthogonal transformation. Okay, so what we know. Each PC, now we are for closed curve. Each PC is or can be represented as an orthonormal matrix, and it satisfies this relation together with this one. What does it mean? We have a group inside, so it means the set of all these transformation is over, I should mention C is in the set of all closed piecewise smooth curves starting at P. So this PC or C in the set of all closed piecewise smooth curves starting at P is a subgroup of O of TPM. Why is it a subgroup? Precisely because when you take two elements, it is still one element or different one, and it's invertible. And the identity is inside. Why the identity is inside? Because you also have the trivial curve, which is stay at the same place. It's a subgroup of the set of all matrices. Yeah, but it's a curve. You stay like this, you are walking at the same place all the time between time 0 and 1. Yes, you're lazy, but still it's a curve. And your vector doesn't move. That's why it's the identity. Okay. What happens if you choose a different point P? If you choose, this was P here. Now, if I choose Q here, and I do the same thing, I take all curves starting at Q, all closed curve. What is the relation between, so I'm going to call this, I'm going to call it the set of PC for all closed curve. I'm going to call it all of P, which is holonomy group at P. What about the holonomy group at Q? Is it the same? No. So what is all Q? What is the relation between all P and all Q? Okay, you can still be lazy and stay, so both contain the identity, I agree. But look, they are related, but they are not equal. Why? Because, in which order I do them? You can always say, oh, a curve like this, I can realize it as, I mean, it's also a curve. I can do this. Take a curve from P to Q. It's connected now. You see why the manifold has to be connected. I can consider this, which is a curve C, then do this closed curve and come back through the same C minus 1. So what is the relation between these two? We have that hole at P is equal to PC minus 1 TC for C, a curve. A curve, we're going to check a curve from P to Q. Because, yeah, it's exactly what I said. Yeah, this curve from P, I can realize it as this one, and back to it. So we start with a curve from P to Q, then we do this holonomy or this closed curve around Q, and then we come back to P. And this is also a curve inside this family. And observe that this is equivalent to PC minus 1 all of Q PC. So it's isomorphic through this conjugation. So it means all of P and all of Q are isomorphic. So you have the same information through the conjugation. It's called the conjugation by PC. However, be careful. If you choose a different C, there is not a unique or canonical way to relate these two things, because if you take a different C and go back, you will still have such a relation, but one element of hole P will be associated with a different element of hole Q. So it's not unique. But still, you have this isomorphism through conjugation by a matrix on its inverse. So it means it's not unique, but still we are going to define something which is almost unique, or unique modulo this. So definition. The holonomy group of M, but now based at P, is defined by all M based at P is simply what I define all of P. I'm not fully happy with this definition, but there is no other one. I mean, they depend on the starting point. You have subgroups of O of TPM, but these subgroups might be slightly different because you can change them by conjugation. This P is called the base point. Oh, base point. Okay. And now you can, okay. This definition, you can take all closed curve. But there is a subfamily of closed curve. Look, my manifold, I made a hole. So there is one closed curve which contains this hole. And I cannot deform it into the lazy curve. So I cannot continuously deform this one into the one which is just staying at the same place. So in the next definition, we are going to construct or to consider only closed curve, which can be transformed continuously into a point. Okay. And I introduced this notion of deformation of a curve some weeks ago, not in this framework, but I mentioned how you can do it. You consider a family of curves, and in fact, you can transform this family into just one point. I don't want to rewrite the definition. It's going to be the same, but if, yeah, I don't think there is a problem. So if we consider only contractible, this is the word contractible, closed curves. So contractible means can be continuously deform or transform into the trivial curve, which is a curve where you stay for 1 minute at the same place. So if you consider only, yeah, really only, if you consider only contractible closed curves, so it means less than all of them, you forget this one, then we have all 0 of P. I don't have to write it. It's the same definition, but only with contractible curve. Maybe I should have, sorry. Okay, no. And similarly, we have also what I defined all 0 of M, like here, based at P. So it means we have, this is a smaller group because we have less curves. No, this is a O. This is not a 0. It's whole. Oh, okay. I did the same mistake. I don't know. It's whole index 0 just to mean the 0 means contractible. The small 0 here is related to the fact that we consider only contractible curves, only the one which can be transformed into the 0. This is a nice notion. I'm going to mention one small result related to holonomy, and then the connection with curvature. A small lemma, I think it's even given as an exercise in some books. M is orientable. Remember, this notion of orientable means you can move along the curve and come back with the same direction. If and only if all of P is inside SO of T. What does it mean? It means the determinant is 1 or not -1. And I have the feeling that it's not surprising, but okay, it's not a proof for any P inside the manifold. Because probably if you could go to determinant -1, it means you have no orientation. But okay.
Go around the manifold.
Okay, it's your job to show this. I'm sure you can find. So it was orthogonal, and S is for special, so it means determinant. The determinant is equal to 1. So before we had O in J, but O means orthogonal. Now if you take SO, it means all have determinant 1. Okay, now what is the relation between curvature and holonomy? There is one statement which is rather vague, and I'm going to give you this one first and then a slightly more precise. You can think about, so holonomy means you start at one point, you do this small parallel transport. But you can take a small curve and you look at how your vector evolve along this small curve. And in fact, the curvature is precisely related to this shift between your initial vector and the one you obtain after the small transformation, the small transport. Or more precisely, the curvature is related to the infinitesimal change of orientation. And when you want to make it precise, you need the notion of Lie algebra. Lie algebra and Lie group and Lie algebra. So first I give you a rather vague definition, and then a more precise one, just to make the link between curvature and this notion of holonomy. So holonomy and curvature are linked. In fact, curvature is at the root of holonomy. Oh, why is it at the root of holonomy? Because if you have zero curvature, like the flat plane, you can do it. Okay, you can do the parallel transport along a flat plane. You're going to have zero holonomy. While if you're on a manifold like on a sphere, and we have seen this picture before, the curvature is not zero, and indeed you're going to have a holonomy. So it's really the curvature is the source of holonomy. Okay, how to see it roughly? I'm not sure it's completely convincing, but okay, we consider X and Y, two vector fields on a manifold M, and we are going to assume I'm not sure I fully understand this notion of what means commuting vector field. I don't have a picture of what it means. If somebody want to, we have a manifold and we know vector fields that at every point you associate a vector. What mean exactly that two vector fields? We have seen this notion before. In general, they do not commute. But how can I represent on a picture two commuting vector field? I don't know. So if somebody wants to understand this relation on a picture, it would be nice. What means commuting vector field exactly? How can I represent it? Probably you can find this on the internet. So I assume that they commute. And it plays a role because the connection, I just mentioned it, I didn't prepare this, but why it plays a role? Because R of xy, do you remember it was this, oh, maybe I don't remember, so I will not write it right now. Okay, so I assume that I have two vector fields which commute. And now I consider the manifold P. Remember, each vector field define flow. So whenever you have a vector field, you have curves along the vector field. Each vector field defines flow and what is called an integral curve. Integral curves. So I'm going to look at this. I have P. I take one vector xp and the curve like this. Then I take, after a certain time, I have a second vector field, and I'm going to consider the flow with a second. So this is, the yellow one is flow given by x, by this vector field, and the y is a flow given by y. We have seen this notion. And I'm going to come back with a flow given by x, and then close the curve with a flow given by y. And I'm going to consider all these of length t. So we consider. And you can do it because you have such a nice picture because they are commuting. We consider this parallelogram based on integral curves. Each curve or each part being of length t, each part of length. There is a better picture in the notes, but it's really you follow a flow, then after length t, you go on a different flow given by y, then after length t, you come back with a flow generated by x in the reverse order, and then you go back to this one. So you have a path. So what you get is you get a curve, a piecewise piecewise smooth curve of length 40. 40 if each of them is of length t. So we have this closed curve, and I can now take one more vector and do the parallel transport of this vector along this closed curve. So I take one vector and do the parallel transport along this. Okay? So we are in the framework. We have a closed curve, and we do a parallel transport. So take z p belonging to TPM and consider the parallel transport of z along this curve. And as before, I'm going to call it dt, denoted by z of t. So we have this closed curve given in terms of these two vector field or their flow, and we do the parallel transport of z along this. Then the derivative of zt with respect to t at 0 is equal to this gradient on nabla y. And I'm not sure I fully understand this. But I told you, this is a heuristic. It's not the precise definition. I guess we can still understand if we look precisely at what means the parallel transport along this, the parallel transport along this, and then we go backward, and this is why we have a minus sign. We go backward here and here. But we have seen this expression, this connection x, connection y, connection x, connection x, connection y. It's equal to minus r of x, y, and I'm going to write a p here, p z t, zp. However, in the definition of the curvature, there was one more term. But the additional term is precisely related to the connection on the commutator. And if the commutator is 0, you have no additional term. So this expression is really this one if you have this additional assumption. So it means this is what I said before, the small holonomy, and this is related to the small holonomy in the sense you take the derivative is the limit when t goes. So you are looking at the generator of this holonomy is related to the curvature. Now there is, maybe those interested can read it. I will not speak about this next week. But keep it in mind. This derivative is like the generator of the holonomy is given by the curvature. The more precise statement is in the note. It's called Ambrose-Singer theorem. You need to work a little bit more because we had this holonomy group of M. It's a group. It's in fact a Lie group, which I haven't introduced and I will not introduce it. But the Lie group, it's part of a different story. This Lie group has generators, and the generators is a Lie algebra. these are the generator of a Lie group. And this Lie algebra is precisely given by these things. So this is this relation, the curvature, so this Lie algebra is at the root of the Lie group, and this Lie algebra is related to this curvature. So there is a precise statement which makes sense with what we have seen, except that I haven't defined the notion of Lie group and Lie algebra. But it's like you should feel that, yes, you need to look at the infinitesimal generator, and the infinitesimal generator is nothing but the curvature. This is what you should keep in mind. Now, if you want to look more precisely, there is a statement. Okay, that's all for today. Do you have any question or remark?